Hello. Welcome to the final project for our RTOS class, Real-Time Embedded Systems. And so this is kind of just the consolidation of a bunch of previous projects that we've done. So namely transmitting IMU, GPS, and live video data from an air station down to a ground station. So there's going to be a lot of similarities between this project and the previous three or four. In fact, in a lot of cases, I was able to just grab and reuse code, which is really nice. So now we can get into it. So getting into the requirements, again, we're capturing IMU data on the Arduino, and we're just using an Adafruit accelerometer. The difference here is that we're sending it to the Raspberry Pi via I2C, whereas previously we were just plugging in via serial port. So that brought its own complications, which we'll get to. And then we're streaming via Wi-Fi, but more specifically TCP connection from the Raspberry Pi to the host. Also, a couple things there that we needed to add compared to the previous time. And then capture GPS and capture live video on the Raspberry Pi. Those two, thankfully, were pretty straightforward since we had already solved these problems. And as you'll see, I just kind of reused terminal commands, which is nice, and we need to make sure that we're not using the same ports. So I'll get more into that later. And then lastly, we're capturing all this on our host and streaming it so we can view it. And again, we're using the FreeRTOS framework on the Arduino. That handles a lot of the race condition handling, and we'll also get more into that. So starting with our hardware setup, again, it's a mass apologies, but we'll start with the Raspberry Pi. So here's our Pi, and it's connected to this battery pack. I've been using the same one the whole time. And this is also going to power our Arduino. And then here you can see is our little camera. It's facing down, but here's the camera plugged into this USB port. And then the GPS right here is plugged into this USB port. I believe the Pi comes with, let's see, comes with four USB ports, which is really nice. Uh, and then, okay, so that's our Pi. And then if you can see over here, we are connecting, this is the SDA, SCL, and ground. So this is going to be our TCP connection coming all the way over here to our Arduino. And I'll get into the pinouts and specific wiring connections later on. And then lastly, we have our Arduino. This is the same wiring scheme that I literally have not unplugged it in like a month or two. This is just plugged into our IMU, our Adafruit IMU right here on this breadboard. So that wired connection really hasn't been touched. So getting into the system architecture. So this one's a bit more hectic than the others, but if we look closely, it's really just a couple projects consolidated into one. So, kind of bouncing back between this slide and our previous slide, here's our onboard station and our ground control station. And so on our Raspberry Pi, we are connected via I2C to the Arduino, and then we have our GPS and video. Something to note is that since we're streaming from a client to a host or our Pi to my MacBook, we need to make sure that we're using different ports for video, GPS, and IMU data. So for GPS, I'm using port 5001, video port 5000. You just need to make sure that there's parity between the script or the program that's sending it out here and the Python script that's listening for it here. Or more specifically for GPS and video, those are terminal commands. There's some really nice Linux tools I'll show, and you give this long command, where the host is, and you also pass it a port. So you need to make sure that that port has parity. So zooming into each one of these components specifically. So streaming video, something to note here is it's a UDP connection, not a TCP. I'm not super knowledgeable about this. I do know that UDP is it gives you speed in terms of how much data you can transmit, but it also comes with the cost of the quality of that data. So with the TCP connection, you're sending data and then you're getting confirmation that that data was received. With UDP, you're just sending. And that makes sense if you think about it. When you're streaming video, you're streaming a whole lot more data than say, lat long out commands. Um, so for just a timing perspective, UDP connection makes sense there. So again, these two terminal commands are just grabbed from our previous assignment. On our Pi, this is the command that we run to send out the data. So you can see that here's the host IP, which is just the IP of my Mac, and we're setting it to port 5000 on my Mac. Conversely, on my Mac, we're running GST launch, UDP, and we're opening and listing on port 5000. Trying to see if there's anything else here. But yeah, main thing to note here is that we're using a UDP connection, and we kind of need that for video, for something like video where we're sending so much data. So GPS, a lot simpler. We're using a TCP connection. Linux has so many helpful tools. I swear every week I find a new one. So this was, sudo apt install c GPS, and we're streaming it to port. This should be 501, or excuse me. Yeah, GPS should be 501. This is just copied from the previous, but I'll show you the demo that we actually use port 501. And then this is what we see on the Mac. I have kind of tough to present this given how many terminals I've got open, but on our host, essentially, we're just running this command saying, NC, pass it the IP address of the Pi and tell what port to look for. So that's 501 rather than 5000. So yeah, here's video, here's GPS. So those, fortunately, I was able just to go back to the code that I used for the previous assignments and run them. Not too many complications or debugging to be done there, which as an engineer, you're always thankful for. So now getting into a bit of a more tricky part, let's talk about I2C. So we have this wired connection between the Arduino and the Raspberry Pi. The first thing you need to do is you need to go to the Raspberry Pi pinout. So you can just Google that, RPi pinout. And you're going to see that here and here, pins 3 and 5 are our SDA and SCL respectively. Then we also need to connect to ground. On the Arduino, fortunately, at least the one that I have the Uno R3. They literally label it, like they write it on the ports, which is really nice. So you don't need to, look Google for a pinout. And also when you're actually wiring the thing, you can always double, triple check that you have the wiring correct. So in terms of wiring, pretty straightforward, but you did need to Google this to figure out what to wire to what. So in terms of what's going on under the hood, so you have an I2C master and you have an I2C slave. So our Pi is going to be our master and our Arduino is going to be our slave. And so on our Raspberry Pi, we have some function like bus read I2C block data. That's just kind of pseudocode for saying, we're telling the slave, hey, send me a block of data. And we'll get into the code later, but we pre-specify how much data is a block. In this case, we're using 32 bits. Yeah, I'll elaborate more on that later when we get into the code, but keep a mental note of that. Also, the callback function executes. So when we request that event, Arduino hears that and it executes some function. Something to note is that it runs in an interrupt context. So going back to the earlier modules of this course, when you hear interrupt, you want to think, you want to keep that ISR short, simple. So really all we're doing, as you'll see in the code later on, is that we're literally just reading raw data from the IMU. So it's like 3 or 4 lines. So yeah, we want to do that because we don't want interrupts to take up too much time, too much resources, etc. And again, as mentioned, we're using a fixed buffer size of 32 bytes. And then we send the data. We use just the wire library. So wire.write, some static method. We call that inside of our quest event function. And that actually is what sends the data to the master. We already got into the RPI pinout. So here I've already showed the terminal commands to stream video and GPS via UDP and TCP respectively. Again, make sure those are being sent on different ports. For some pre-setup troubleshooting, you can run sudo i2c detect -y. There should actually be a 1 here. So this is the terminal command I ran just to say the Raspberry Pi saying, yes, I see that I am connected to the Arduino via I2C. Uh, so this getting into this code, this is pretty simple. We're establishing an I2C connection. We're establishing a TCP connection. So this is receiving the data. This is sending the data. This is more just TCP initialization. Um, and then, yeah, we're reading from the buffer, 32 bytes at a time, and then we're sending it. The main thing that I added in here is that if you look at this line, IMU data equals, join char byte, this list comprehension right here. What this is doing is this is stripping any unwanted bytes. So a problem I was running into is we would get, or at least we're intending to send GX, GY, GZ, AX, AY, AZ. And then at the end, we'd see some like random symbols, ASCII symbols, whatever it was. So a way to get around that, to kind of filter and clean the data, is we're just stripping all bytes beyond 128 bytes, or bits, excuse me. So 32 bytes, and we're stripping it here. So that way, when we send it down to the ground control station or my Mac, we don't need to worry about data formatting. And actually, I believe I threw in some extra data formatting, confirming it's in the right format on the ground station just for extra safety. And yeah, so here we're sending over Wi-Fi, little delay to avoid any data flooding. I have the baud rates set to 9600 for all these. I'd imagine you can get it higher. But just for simplicity, buffer flooding, all that stuff that I didn't really feel like, getting into, it suffices just to do a baud rate of 9600 bits per second. And then obviously we're closing our sockets at the end. So the RTOS design, again, is super, super simple. We're reading from I2C and we're sending over TCP. So this, if you look at my previous like 3 presentations, anytime we're reading IMU data, fortunately the code was largely just, copying, which is very nice. So again, we have this super handy RTOS function where we create a function pointer or a task function pointer, some human readable description, stack size, no parameters. We're not passing any parameters. We set a priority between our tasks. And we also set this last one in null. We don't use that. Again, the risk of being redundant, we're using semaphores. So while one task is executing, it takes a semaphore, it does what it needs to do, and then it returns a semaphore so that the other task can run. And so this is just running continuously. Yeah, not much of a need to go more into detail here. This is, kind of the core of our previous projects. So I will move on to streaming over I2C. Let's see. So yeah, we install a bunch of libraries on our Pi, namely PySerial, which handles a lot of the things for us. It abstracts away a good amount of stuff. We're streaming to host via TCP, and the host is listening and plots in real time. Also, I kept in the Madgwick filter. I can bring over that code. So yeah, so we're running it through a Madgwick filter, which is going to resolve some of our Euler angles. And, as you see in the plots, it's a lot smoother, a lot better to read. Yeah, I'll get into the code in more detail in a bit. So for demo, I'll throw in this link once I finish recording this video. Here's our roll pitch. So this is kind of our end result. And then also, as we see up here for video, I can actually run the video here. I'm inside right now, so the GPS won't really pick anything up. I'll do this in parallel while I explain the others. But okay, so getting into the Arduino code, let's see how much stuff we really changed. I don't just want to repeat over and over again. Something to note, do we use volatile memory? No. So, okay, so we don't even use volatile. What we could do is we set AX, AY, AZ, this whole line, we set this to volatile, which tells the compiler, don't optimize it, don't read it, don't cache it in the CPU cache, read it from memory each time. And that's going to protect us against any race conditions. So if, we're not going to be reading outdated values. um, or whatever. So yeah, this is pretty straightforward. Something to note here is that we established some buffer size, and I set that to 32 up here. And so this is basically saying we're using snprintf, which is the C function, right to this buffer of this size, and we're just formatting the data as ax, comma, ay, comma, az, comma, gx, comma, et cetera, et cetera. And also something that we need to do is ensure that our buffer is not exceeding the maximum buffer size of 32 bytes. So as you can see earlier in this code, you want to do the size of each one of these, add them up, and make sure that it's not overflowing. So that's really the main checking to do. Yeah, so nothing too complicated there. And here is our Raspberry Pi data, which I've already gone into. Remember, for whatever reason, even though I was doing that check, we're still seeing some extraneous bytes at the end. So this line right here, stripping the string that we're getting, that solved it. And then we're sending it to our host. And lastly, in our host, I've already, I just pulled up the code, but here's really what we're seeing. Data, read I2C block data. And yeah, so thank you for watching.